A team of physicists led by Regina Demina, a physics professor at the University of Rochester, has made a significant discovery regarding quantum entanglement, the phenomenon Albert Einstein famously called spooky action at a distance. Entanglement involves the coordinated behavior of tiny particles that have interacted but then separated. When one of these particle pairs has its properties like position, momentum, or spin measured, it instantly changes the corresponding properties of the other particle, no matter how far apart they are. Essentially, the state of an entangled particle, or qubit, cannot be distinguished from its twin. Quantum entanglement has been observed among stable particles like photons and electrons. But Demina and her team have broken new ground by finding entanglement for the first time between unstable top quarks and their antimatter counterparts, persisting at distances beyond what information traveling at the speed of light could cover. Specifically, the researchers observed spin correlations between the particles. Thus, the particles demonstrated what Einstein described as spooky action at a distance. This finding was reported by the Compact One Solenoid CMS collaboration at the European Organization for Nuclear Research (CERN), where the experiment was conducted. The report states, confirming quantum entanglement among the heaviest fundamental particles, top quarks, opens a new path to exploring the quantum nature of our world at energies far beyond our reach. CERN, located near Geneva, Switzerland, is the world's largest particle physics lab. Producing top quarks requires the extremely high energies accessible at the Large Hadron Collider LHC, which allows scientists to send high-energy particles racing around a 17-mile underground track at nearly the speed of light. Entanglement is a cornerstone of the rapidly growing field of quantum information science, with wide-ranging implications in areas like cryptography and quantum computing. Top quarks, each as heavy as a gold atom, can only be produced in colliders like the LHC, making them impractical for building quantum computers. However, studies like those led by Demina can shed light on how long entanglement lasts, whether it transfers to the particle's daughters or decay products, and what ultimately disrupts it. Theorists believe the universe was in an entangled state after its initial rapid expansion phase. The new result observed by Demina and her team could help scientists understand what leads to the loss of quantum connectivity in our world. To explain her team's findings, Demina recorded a video for CMS social media channels, using the analogy of an unstable king in a distant land, whom she named King Top. King Top learns that his kingdom is being invaded and sends messengers to alert his people to prepare for defense. But then, as Demina explains in the video, he changes his mind and sends messengers to order retreat. He keeps flip-flopping, and no one knows what his decision will be next, Demina says. In this kingdom, the only one who understands King Top's mood swings is the leader of a village known as Anti-Top. She continues, they know each other's state of mind at any given moment, Demina says. Demina's research group includes herself, graduate student Alan Herrera, and postdoctoral researcher Otto Hindricks. Demina was part of the team that discovered the top quark as a graduate student in 1995, later, as a faculty member at Rochester. She led a team of scientists from across the US in developing a tracking device that played a crucial role in the 2012 discovery of the Higgs boson, a fundamental particle that helps explain the origin of mass in the universe. Rochester researchers have a long history at CERN as part of the CMS collaboration, which brings together physicists from around the world. Recently, another Rochester team reached a significant milestone in measuring the electrowake mixing angle, a key component of the standard model of particle physics, which explains how the building blocks of matter interact.